So actually, the non-equilibrium initial condition have the lower symmetry, as I indicated. So that was indicated by Aresen et al., Italian group. And we can eliminate the slowest eigenmode by unitary transformation. So in such situation, it is easy to observe the Pemba effect. This is what indicated by Carroll et al. And the paper is very primitive, so that we can improve this paper. And non-Markovian Pemba effect as discussed by the Indian guys. So this is also interesting one. And it's very counterintuitive result. And let me show you the very briefly ongoing project with the French guys. So what the analysis of the exactly solvable model in terms of Honka-Planck equation, or in the first scenario means starting from the initial equilibrium conditions with Frederick van Beelen and Raphael Chatteriti. And another one is the condition of the occurrence of the Pemba effect based on the correlation function, as well as non-Go theorem with a narrow Oga and the Soskato. Look at this paper. And let me summarize my talk. And so we demonstrate the occurrence of the quantum Pemba effect and with Anderson model, Hatton model. Difference of relaxation rate in equilibrium, non-equilibrium initial condition is important. And if the exceptional point exists, exceptional point observing the quantum Pemba effect is easier than the absence of the exceptional point. Multiple quantum Pemba effect can be observed easily. We demonstrate some modularization Pemba effect as a general condition of the Pemba effect. See this paper. Thank you for your attention.
Pinaki and Arnav, can I put students in the spot and ask students to ask questions? Are there students in the audience? I know there are in one. Can a student ask the first question? Any question? You guys understood everything? Okay. Okay. Next, for Rajesh's talk, I'm going to, so pay attention, I'm going to ask a student to ask questions. Other questions from the audience?
Why did you say that there's no temperature in that experiment?
Experiment on in a classical experiment or okay. Yeah, quenching. So they have used the quench. So initially they have prepared a very hot temperature defined by the distribution function and quenched into the low temperature. And so if the initial temperature is not high enough, the probability to okay, this is an experiment, not the experiment. This is a cartoon. So this one? This is exactly correspond to this situation. So they have analyzed the master equation.
No, I understand.
But you said there's no temperature. So is there a temperature in their model?
In that model, there is a temperature. At least.
It says there is no temperature.
I mean, they have only discussed such kind of the crossing. You are using the distance or monotone measure, Kerr divergence. They have not discussed the crossing of the temperature. So sorry, misreading description. So.
No, but temperature is not defined in that range.
Yeah. So, for example, my analysis introduced a temperature. Of course, this is a not unique definition of the temperature. So, but the Fitch is used for the thermodynamics. So it's different from the conventional approach. So that is what I wanted to say. Yeah, right.
Based on that, you could have taken any budget for this, right?
Yeah, so, yes, this is, of course, the controversial part. Then, if we believe the local equilibrium description is correct, then this definition is reasonable. But the system is very small, and we cannot justify that to be used this temperature as a measure. But actually, this is not monotone measure, so we may have to use K divergence instead of this one. But K divergence also exhibits similar behavior.
Okay?
We also have some other possibility.
Yeah, maybe we follow up
Discuss
later on.
later.
Thanks a lot, Lisa.
Okay, thank you very much.
The next speaker is our Rajesh, and his last year intent of his talk is large regression function for cluster cluster.
Okay. Many thanks to Pinaki and Arnab for organizing this meeting and bringing everyone to IMSC. Okay, I'll talk today about aggregation. This work is done with Subhashri, who just graduated, and based on this paper. So aggregation of particles that are transported is the dominant physical process in many physical systems. So I'll give you a few examples I'll just show to show that aggregation is ubiquitous. So consider a river network where the river starts from the mountains and they form tributaries which join to form bigger rivers and finally reach the sea. If I look upon this as time axis and this as x-axis, then these things joining together is like aggregation. Two random walkers come and aggregate together. Another example is Saturn rings, where you have these ice and dust particles moving around. They collide, shatter, and sometimes they aggregate and maintain some non-equilibrium steady state. Both of these are at the scale of kilometers. Then at the micrometer scale, you have an example of cancer cells when put into a medium, aggregating together to form big clusters, increasing their virulence, for example. And this one is an example from dust particles forming soot. And finally, a couple other examples from other very different systems. One is from ductile fracture, where you form voids, and these voids coalesce to form bigger voids till the system fails. And another example from polymers. Polymer aggregation is common in Alzheimer, mad cow disease, and so on, and is crucial to avoid. So I showed some slides to show that aggregation is ubiquitous. Now there are two features in all these processes. One is the transport to bring clusters together, and the other one is when they come to contact, they aggregate. So when you model, you have two options. Either you model transport and aggregation separately, or you combine them into an effective collision kernel. Okay, you just say that the rate of collision is something, and they collide and become a bigger particle. Now, I will take this, in this talk, I will take this particular approach, and I'll tell you what I mean by that. So let me first define a model that has been studied for many years. I'll call it cluster-cluster aggregation. So at some point of time, let there be a collection of particles, and each particle is labeled by some mass m1, m2. In general, a mass which is integer. mass. And then the system evolves in time by a simple, just one dynamical process. Two particles coagulate at some rate to form a bigger particle. So two particles become one particle, but mass is conserved. And the rate of collision, I'll call as collision kernel. In general, it could be mass dependent. Okay? It depends on both the masses colliding. And you start with, let's say, capital M particles of mass 1 or mass m naught, but we measure everything in terms of that mass, so we can set it to 1. And in one collision, mass is conserved, the number decreases by 1. Okay? This is the model I'll focus on. Now, so let me give you an example of what is a collision kernel. So if I look at ballistic particles, particles that move in a straight line and they collide to form a bigger particle, then if we look at the rate of collision, you can imagine it is proportional to the relative velocity and it's proportional to the radius of cross section, area of cross section, which is r1 plus r2, the radius of the particle to the power d minus 1. Now in kinetic theory, we normally write this difference as square root of the RMS velocity, and if you assume spherical particles, then this becomes mass to the power 1 by d. And then you can convert the velocity to mass using momentum conservation to get the collision kernel which you use in kinetic theory. Okay. So likewise, depending on the system you study, you can create an appropriate collision kernel. Now, this particular problem of aggregation has been studied for a long time, pioneered by Smoluchowski in 1917. Okay, and he proposed this equation, the coagulation equation, which is only an enumeration equation. Okay, so let me just describe. So you look at the number of particles of mass m at time t. So there's a distribution, and this distribution is evolving stochastically. But the idea is that to write a mean field equation for the mean mass distribution. So you ask, how does it change with time? So if I have a particular at one instant, it can change due to two terms. One is when two particles collide, which are different from mass m, and they combine to form a mass m. So you write this as density of particles of mass m1 of mass m2 colliding to form a mass m with this corresponding rate. And then there's a loss term. You had a mass m, it collided with another mass m1, and that to form some other mass which I don't care, and that loss term comes with the density of particles of mass m and the density of particles of mass m1. Okay. So this is you can write this down by inspection. Okay. And this, since each collision conserves mass, this equation also conserves mass, but sometimes it doesn't. Yeah, so this particular equation is a mean field equation. It ignores all fluctuations. So as time goes on, larger and larger masses are created. The typical mass happens to go as time, as t. Here is exponential in t, and here there's something funny happens. So I will just tell what's this funny thing that happens for this product kernel. So for the product kernel, when you solve for the mass distribution, you get some answer. Now the precise form is not important. But if I look at the second moment diverges at time t equal to 1. Okay, and this transition in the literature is known as the gelation transition. So what happens beyond this transition? You have to find the solution. The Smoluchowski equation is the solution for infinite mass equation. So you have to find a solution for finite mass, and this solution is a complicated solution depending on something called Mallow's rule. What is known for the Smoluchowski equation analytically? There are a lot of numerical techniques for solving the equations depending on the kernel you study, but that I'm not focusing on in this talk. So so now what I am going to focus on in this talk is what are the probabilities of rare events. Okay? So to remind you, the Smoluchowski equation does not address any fluctuation beyond the mean value. So, so for example, if I were to look at just the number of particles, not the mass distribution, and I solve the Smoluchowski equation, I get this black line. it decreases with time. But I could ask, what's the probability of this red line, or which is away from the typical? Okay, this I will call as rare events. So if I fix a time, I could ask at this time, instead of the typical value, I get the mass, the number of particles to be much larger or much smaller. Likewise, if I fix a particular density, at what fraction at time does it reach that particular number of particles? Now, if I want to define some quantity that captures this, I'd like to ask, what is the probability of starting with m particles, finding n particles at time t? So if I can answer this question, then I describe the stochastic, the model I described completely. Okay. As now, usually in the literature, when you want to study events away from the typical, that is described by something called the large deviation function. So I sort of assume that this audience is familiar with large deviation function, at least they heard the word before. So in the remainder of the talk, what I will do is I will tell you how to calculate this probability of having n particles at time t, starting with capital M particles, and present an exact result for the 3 kernels for which the small source equation was solvable. And so let me summarize the results of the talk. The remaining talk will be a bit technical, but I will summarize what we find here. So what we find is, if I look at this probability, it has the large deviation form e to the power minus the total mass in the system into function of the fraction of particles remaining and time scaled by n. Okay. Which means that I can identify m as a rate and f as a large deviation function. Now, this particular form can be shown for any kernel. Then the exact, but the form of phi, what is the precise form of phi solving such a problem? So so at any instant of time, if I ask what is the configuration, so I can ask how many particles are there of mass 1, mass 2, mass 3, and mass n. If this vector tells you the creation operators to write the master equation as a Schrodinger equation, like a Schrodinger equation, and then convert that into deriving effective action for the problem. So I'll just give one slide description of how this is done. So the key thing is to introduce a wave function to define this wave function. Then the master equation, after some manipulation, can be written like a Schrodinger equation, okay, where you have to introduce in terms of the annihilation and creation operators. So for example, for the problem for aggregation, the Hamiltonian looks like this. So the only difference is that this Hamiltonian is not Hermitian. Otherwise, it has the form of a Schrodinger equation, and with a solution which has this form. Now, the relevant quantity we were interested in is what is the probability at the final time of a certain configuration. That happens to be some particular inner product with this wave function. And you get some complicated expression of this kind. Finally, you introduce coherent states to convert and to derive an effective. These are all well-known procedures, but once you do this, then you find that the probability that we want of finding n particles at time t can be written in terms of a action S, okay, provided you scale your time and your n in this manner. That is what I said, that if you in this scaling form, there's a large deviation form once you scale like that. Okay, it looks a bit messy, but the point is there's an action which has a certain form in which the boundary initial condition and the final condition comes in. So the point is the action depends on the dynamical process as well as the initial and final condition. That is important because these final and initial condition finally contribute to the large deviation function quite a bit. Now, if I were to stare at this equation, it has the form e to the power minus m times some action. And in the limit m going to infinity, all you have to do is minimize the action to get the leading form for this probability. Okay.
N large and m large keeping
Yeah.
the ratio fixed, but you also have this t small m large keeping the product t
Yes.
fixed. So in some sense, a short time result or
No, even in the small Chaucy equation, if you don't do the scaling, you don't get a reasonable, sensible answer. Even in the when you take m going to infinity, you have to scale. That time is already scaled in that fashion.
so.
For example, in if you look at the product kernel, in the gelation occurs at 1 by m. So only when you scale m with t, you get a finite gelation time.
Is there any simple way to see why this 1 over m scaling comes in? What's the time scale?
Why? I don't know, but I can think and tell later. No, even for the sum kernel, you have to scale. So now there's an action we want to minimize, and then the minimization is given by the usual Euler-Lagrange equation. But with some funny boundary conditions. So there are two variables z and z tilde, and they obey boundary conditions of this kind. And so the Euler-Lagrange equations have to be solved for z and z tilde with these boundary conditions. Now it turns out that with some effort you can solve for these three constants, sum and product kernel. So I'll just tell you the results for them and show that with simulation that they are the right answer. So the first claim is that so if I go back to this equation, I minimize this, then the claim is that if I take the logarithm of this and with m, there's a finite limit phi, which is a rate function. This is true for arbitrary kernels. Okay. Now for the constant kernel, you can find the solution. The solution depends on one more point I have to tell. So once you have an Euler-Lagrange equation, the Euler-Lagrange equation conserves the Hamiltonian. So if I start with a certain energy, that energy is conserved. There is a parameter E, which is you can control, and that E is what comes in this equation. And the form of this equation is complicated. There's no particular sense in trying to understand what this form is, but the large deviation function, when plotted for fixed time and changing phi, looks this solid line. Now the E equal to 0 corresponds to this bottom, which is the typical answer, which is so the small Chaucy equation corresponds to this particular point. Okay? And the data is from a simulation which is directed towards determining low probabilities in such problems, okay? And they match quite well. In addition, you can ask, given a particular phi and a rare event, what is the trajectory? And that trajectory also we can compute. What is the mean mass, mean number of particles as a function of time for different tau typical. So I can look at tau typical, I can look at times which are 5 times tau typical or tau typical by 5, and you can compute the trajectory that contributes to the large deviation function. Yeah, E comes in, it is determined in terms of the boundary conditions, but in this particular case it's complicated to calculate that. Similarly, for the sum kernel, you have a simpler form for the large deviation function. This is the large deviation function. This point corresponds to the Smoltowski answer, and you can see that the answer matches quite well. And likewise, you can compute the trajectories for given any rare event, you can compute the trajectory for that. So these two are, so they are just some functions, and they are not so interesting. So finally, in the product kernel, we could calculate the large deviation function in terms of the final, the phi, the tau. But there's a complicated expression in terms of something called Mallows-Riordan polynomials. Okay? And so when we evaluate this, see, for example, if I look at tau equal to 3, this is much beyond the gelling time, but the large deviation function one can calculate even for them that time, and it matches quite well with the simulation. Ignore these parts here; these are sort of finite size effects from the simulation. Okay. The interesting part is, if you take the large deviation function and take a second derivative with respect to phi, it happens to have a singular behavior. So I am plotting the second derivative with respect to phi, and there is a jump at a certain phi. So I am fixing tau. I am plotting as a function of phi, and it has a jump singularity. Okay. And these are for different times, fixed times, 3, 2.5, 2, and 1. And what happens, so there must be some difference of behavior in the most probable trajectories on the right and the left. And on the right, we find that the most probable trajectories have no gel, and on the left, you find that the most probable trajectories have a gel. So that's a numerical finding. So that causes a singularity in the large deviation function. So that so I have quite a bit of time. So let me now, so I can go slowly here. So aggregation is an old problem. It's an infinite species problem. If I consider each mass as different, it's an infinite species problem. And so we are able to compute LDF for 3 standard kernels, and we could explicitly show it is singular for the product kernel and expect it to be singular for all gelling kernels. What I didn't say is that we can compute many more things like mass distribution along a trajectory. So why is this important? The importance comes from the fact that aggregation has both experimental and theoretical interest for a long time. But this angle, that going beyond the mean or the fluctuations about the mean, has not been possible up to now. And therefore, this opens up a new paradigm in aggregation. Yeah? So that is the main contribution. Now, so let me spend some time on some of the directions we are looking at. So one direction is we are able to solve only for 3 kernels. So you can ask, can you have Monte Carlo algorithms which look at rare events in an efficient manner? So for that you have to look do what are called biased Monte Carlo simulations. But for aggregation, it's a bit complicated. So we had come up with some complicated algorithm for biasing the simulation, which we published in this journal. But now with the calculations in hand, one thing we realized is that for reasonable kernels in C. So I think this seems possible. This is one direction we are trying. Then one thing I could not explain because of the complicated nature of the derivation. For the product kernel, when we try different derivations of the action, so that is one direction that is good. And other questions which we are interested in trying. So I was looking at P of m, n, t, where n scales with mass to find the large deviation function. But you can ask when this n does not scale with mass. For example, what's the probability of having all things clustering at time t? Now the scaling will be different. The calculation is similar, but can we calculate the probability of fluctuations about them? This also seems calculable within this procedure. And so another interesting problem of aggregation is when there is aggregation, but there is also input of particles to reach a steady state. So can the formalism be generalized to compute them, both the input as well as the space involved? And other obvious generalization is, instead of binary collisions, we look at k-nary collisions. This we wrote a recent paper on that. One more thing we are very much interested in is, so if I look at generic kernels, so I look at a kernel, I look at a kernel which is characterized by two exponents mu and nu. So, for example, for constant kernel mu is 0, nu is 0. Some kernel mu is 0, nu is 1. And for product kernel nu is 1, mu is 1. So, we have a phase diagram like this. This is from the analysis of the Smolchow's equation. So, it says that when mu plus nu is less than 1, there is no gelation. In this particular area, bounded by the sum and the product kernel, there is gelation, but at finite tau. Then there is, in this region and this region, there is, the moment you start the simulation, there is a gelation, instantaneous gelation. And here, I don't know the exact meaning of what this says. It says no solution, but it also is, I think all the particles become one, I don't know. So what we were trying to do was to ask, if I work with finite masses, not infinite masses, can we make sense of these regions in terms of large deviation function? So for that, you have to write some Monte Carlo codes which are a bit, go beyond the regular. It has to be more efficient with some algorithms, so which we have succeeded in doing. So we are hoping to investigate not just these 3 points, but the remaining points numerically. That is the point, and I'll stop here.
In one of the slides, you talked about finite size effect. So, can't we get rid of the finite size effect by increasing the boundary?
Which? Yeah, so this one I said. Yeah, so I didn't describe the algorithm that we use. So it's a bit time consuming, and so for example, on the left, if I keep phi fixed and change time, those simulations you can see are very clean. But when I fix tau and change phi, there's a problem. So the simulation, how it works is, you take a trajectory from time 0 to t, and there's a trajectory that follows. Fix the 2 times, and then you make perturbations in this trajectory. And then sometimes when you make a perturbation, then for it to equilibrate further, it takes a lot of time. So which is the difficulty here. So one could improve, but one has to. So the alternate algorithms we are trying seems to be overcoming this problem.
Other questions?
So my question is with the toyability formalism. So if I understand it correctly, you're going from like a discrete model to a continuous model and take some kind of limit, right?
No, mass is still discrete in the action. It is integer. If I were doing a lattice model for with space involved, there I can take the continuum limit in the action, but I need not take there also, but I could take.
So is phi not like a field here, or is that still?
The z tildes are those are continuous. Z tildes are so for each mass there is a z and z tilde, and the z tilde themselves are continuous, but the m itself is discrete.
So also when you get the action, like is it always possible to see what is the corresponding stochastic differential equation to that?
No, if you want to find the corresponding stochastic differential equation, some of the actions when you get, you can do the Hubbard-Stafford transformation and get back the stochastic differential equation. But some actions you cannot. You cannot find. There's no obvious way. But depending on the reaction diffusion system you're looking at, you might or might not get.
Okay, so I have an experience to analyze the cluster-cluster aggregation based on the derivative homology, and it looks your theory is only applicable to the mean field, the infinite dimensional mean.
No, you can include.
But that is so. If you are interested in the finite dimension,
Mhm.
including the fluctuation effect, so it must play, the dynamics must play the role. For example, original Doepeletier formalism is based on the diffusion cluster aggregation. So if you are interested in the ballistic aggregation, it should be different from the diffusion. But I don't find any dynamics in the process. This is one question. Another one is that I found limitation of the such such method because that method cannot describe the shape of the clusters. So the the original field of description assumes that the cluster is a spherical, and including the effect is a cluster aggregation kernel is involved. Describe effectively the effect of the shape or something dynamics, but this is not the case of the real description. Is it possible to describe this
So the first question. So there are two things contributing to fluctuations. One is just the fact that from stochasticity of the reactions, and one is coming from the transport, like diffusion. Now, so that's why I said in the first process, I'll take the approach in this talk where the kernel incorporates the transport into the in this. So yeah, these are like in chemical reactions. So the point is that it has not been possible to compute even this with ignoring diffusion. It has not been possible to calculate. Now you can ask, if I include diffusion, what will happen in this? So then the action you can write for that. But when you write the Euler-Lagrange equation, it becomes partial differential equations. So then it becomes difficult to compute. But then the way people compute in other, I don't know, in symmetric exclusion process and all, I realize that if you look at the Laplace transform of the probabilities, and then you do an expansion in that, you may be able to compute them order by order. It is possible. That's I do not know. But the point is, you can write the same Euler-Lagrange equations with diffusion put in. Solvability is a problem. Now the second comment about clusters becoming, I agree. This is the dilute limit of that, and if you include space, you have to do a simulation. You cannot do anything else. No, not space. If you include complicated geometry for the clusters, you have to do a simulation, and the low dilute limit is described. The scaling laws are described by these problems, but not the time when it becomes too big.
See, you said this for this product kernel, this different approaches leads to different steps of the function. Like, I mean, this is still in the disloyalty formalism, or like what kind of these different approaches?
So the when you derive the action, you can explicitly take into account the conserved quantities. So when some term comes, you can replace it with terms of total mass and so on. Or you can just follow the procedure without worrying about that. Now these two give slightly different actions. Now for this, you can follow the same procedure for sum and constant kernels, and there the answers it doesn't matter. The answers come out to be the same. But when a gel is present, it seems to matter. So that is the point. In the term you ignore in these things, when a gel forms, I have to tell you so there's an ambiguity in the derivation. Ambiguity.
Yeah, I'm just curious to know, is there any aspect of this rate function, the distribution function, which is kind of universal, that is independent of the precise form of the kernel?
So that is exactly this particular. So we know these 3 points. So what we'd like to, as of now, I cannot tell. But what we'd like to do is explore, for example, this region here, and ask which features of for example, the large tau limit, are they dependent on the kernel, or they are independent of the kernel and only dependent on the region? For that, we have to do a lot of numerical things to look at. But this question I cannot answer otherwise. Other than saying maybe that If I look in this entire region, the LDF should have a singular behavior when a gel is present. I think that is true.
You said product kernel different approaches give different action.
Hmm.
Do you mean that there are different solutions to Z and Z tilde when you use those equations?
No, the form of the action itself, one extra term comes. I can show you.
Okay.
So depending on that, the solution, the Euler-Lagrange equation changes slightly, and one of them, they both match for
So
small
that then you get different equations for the Z and Z.
Z tilde, and they match for short times but not for large times.
Okay, that's weird.
Yeah.
And then the other thing is that, okay, this question about like including space and all that, so can you do that with an effective time in the kernel? There are no known time-dependent kernels which have solutions at all. Like, I mean, these collision kernels,
Yeah, I don't know.
there are no, maybe there is no such.
No, I do not know.
Any other questions? Can I ask one last one? Can you add, like instead of just having aggregation, if you go back to your own models?
Chipping.
Yes. Can you do something?
Yeah, no.
You can, like, can you envision doing something?
Yeah, the fragmentation always is a problem. Input is easier.